Okay, guys, this figure is going to push you um, mentally, so you're going to have to hang with me. We're talking about another dihybrid cross. We're going back to Mendel's pea plants, and we're using the two traits of seed color associated with seed texture. And so the seed colors we've already talked about are yellow and green. The seed textures are smooth and wrinkled. So Mendel started with pure breeding plants that were yellow and smooth, and he started with pure breeding plants that were green and wrinkled. Now, when he crossed these two lines, all of the offspring were yellow and smooth. So that meant yellow and smooth were the dominant traits. So if we go back and apply allele symbols, I would have yellow being dominant and smooth being dominant. Now, they've designated the smooth as using the R symbol, so we're just going to go along with their symbolism. But another option would have been putting a big S, and over here a little s, little s. So different authors will do it different ways. So yellow is dominant, smooth is dominant. We had pure breeding, so it's homozygous dominant. The only genotype possible for my green and wrinkled would be recessive, homozygous recessive. Now, when meiosis takes place due to independent assortment, these particular gamete types will be produced. I get one allele from each gene. So I'm going to get a dominant Y and a dominant R here. I'm going to get a recessive Y and a recessive R here. So at fertilization, the only genotype possible is a double heterozygote. Big Y, big R, little r. Now, the phenotype associated with that would be yellow and smooth. Now, don't worry so much about this side. Let's focus on this side. So if we have independent assortment taking place in the next generation, that means what happens at the Y is independent from what happens at the R. So I would expect to produce 4 gamete types. Remember, each gamete has to have one allele from each gene. So I could get big Y, big R, big Y, little r, little y, big R, little y, little r. Now, the probability of getting any one of the Y alleles is 1/2. The probability of getting any one of the R alleles is 1/2. So therefore, the probability of any of these gamete types is going to be 1/2 times 1/2, which would be 1/4. So you can see I have the 4 gamete types here, and again, a probability of 1/4 for each one of those. And I have the same thing going across the top. So since I have 4 types of gametes being crossed, my Punnett square, which again represents the outcomes of fertilization, would need 4 rows as well as 4 columns. So inside each one of the squares represents the products of fertilization. So here it would be dominant, dominant, dominant for the Y, heterozygous for the R, and so on. Now, if you set up all 16 of your outcomes, you'll notice that for all of these that are yellow, you have at least one dominant Y. So that means that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are going to have the yellow coloration associated with them. Okay? Now, if you look at the green, I've got 4. So you notice that it's 12 to 4, which is 3 to 1. So 3/4 are yellow, 1/4 are green. If you go back and look at the other trait, which is the smooth versus wrinkled, you'll see that 3/4 of the offspring are going to be smooth, 1/4 would be wrinkled. So we have 2 3/4 to 1/4 traits segregating. Therefore, if we go back and ask what's the probability of getting a yellow smooth, it would be 3/4 times 3/4, which is 9/16. So if you go through and count yellow smooth, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of the 16 squares are smooth and yellow. If you look at the probability of getting yellow and wrinkled, that would be 3/4 for yellow, 1/4 for wrinkled, which would be 3/16. So if I look for yellowed wrinkled, I have 1, 2, 3, which is 3/16. If I look for green and smooth, again, the probability of getting green is 1/4. The probability of getting smooth is 3/4. So that's also 3/16. I see again I have 1, 2, 3 categories that fall into that. So it's 3/16 for that. the probability of getting green and wrinkled is 1/4 times 1/4, which is equal to 1/16. And you can see I only have one of the green wrinkled phenotypic categories. So this is how we get the 9 to 3 to 3 to 1 ratio. And you can see Mendel's numbers were very close to our expectation. Now, how would you tell that? What you would need to do is add up all of these numbers and get a sum. And then if you take the number observed and divide it by that sum, that will be close to the quotient of 9/16. These two would be close to the quotient of 3/16, and this would be close to the quotient of 1/16. So again, this figure is going to take some time for you to understand. I suggest you sit down and draw it out on your own and make sure that you can demonstrate how the results in this particular figure parallel the results that we saw in the previous figure.